We're going to do a couple of examples of calculating limits using L'Hopital's rule. So here's one, calculating the limit as x approaches 1 of natural log of x divided by x minus 1. And I spoiled it by saying we're going to use L'Hopital's rule, but we need to check that this meets the conditions under which we should be applying L'Hopital's rule. So I'm going to look at this limit as x approaches 1 of natural log of x divided by x minus 1. And if I try to do direct substitution, I can see the denominator goes to 0 and the numerator also goes to 0, since the natural log of 1 is 0. So this is an indeterminate form of type 0 divided by 0. So we can say this is equal, under L'Hopital's rule, to the limit as x goes to 1 of the derivative of natural log of x is 1 over x divided by the derivative of x minus 1 is 1. And now we can evaluate that limit by direct substitution. If x is 1, then this whole thing becomes 1. And I want to double check by graphing this that limit makes sense. I have graphed it and I have a picture of that graph here. So the limit as x approaches 1 of this function, it looks very much like the function is in fact 1. But if you were to drag your cursor along that curve in Desmos, you would see that it's actually undefined at x equals 1. But this is a removable discontinuity, which basically says we could just define that one value to be 1, and then we would have a continuous function. All right, so let's look at this next one. We're looking at the limit as x approaches infinity of natural log of x divided by square root of x. Now, natural log of x looks like this sort of thing, and it does actually go off to infinity. It looks like it might have an asymptote, but keep in mind that this is the inverse of the exponential function, which has a domain of all real numbers, which means that the natural log should have a range of all real numbers. So this piece goes off to infinity. So the larger x gets, the larger the natural log of x gets, and it grows without bound. And also square root, if you put in larger and larger values of x, the square root also grows without bound. So this also goes to infinity. So this is our first one so far where we have a indeterminate form of type infinity over infinity. So let me write that, indeterminate of type infinity over infinity. So this is equal, under L'Hopital's rule, to the limit as x goes to infinity of derivative of natural log of x is 1 over x divided by the derivative of square root of x is 1 over 2 square root of x. So let me rewrite this as, instead of dividing two reciprocals, this is the same as the limit as x goes to infinity of 2 square root of x divided by x, which is the same as the limit as x goes to infinity of 2 divided by square root of x. And as x grows larger and larger, that means I'm dividing by a larger number, and so this limit is going to be equal to 0. So looking at, again, I want to look at the graph of this, and I want to say when I originally graphed this, I had to manipulate the graph because we were looking at the limit as x goes to infinity. And so I changed my viewing window to include very large values of x. And also I noticed that, the values of the output values are going to be close to 0. And so I had to kind of zoom in on the y values. Zoom out on the x values and zoom in on the y values. So here's a picture of that graph, and it looks pretty good. Like, it looks feasible that this limit is 0. All right, let's do one more example. The limit as x goes to 0 of tangent of x minus x, all divided by x cubed. So, tangent of x at x equals 0 is 0. X is 0, and this is all 0. So this is an indeterminate form of type 0 over 0. So I can apply L'Hopital's rule. So I'm going to say, I'm just going to write equals. I'm not going to repeat that. So this is equals under L'Hopital's rule. The limit as x goes to 0 of derivative of tangent is secant squared of x. The derivative of x is 1, and the derivative of x cubed is 3x squared. So now I want to evaluate this again by direct substitution. At x equals 0, secant is 1 over cosine, so cosine of 0 is 1, so this is going to 1, and so the whole numerator is going to 0, and the denominator is also going to 0. So this is still an indeterminate form of type 0 over 0. So I'm going to say, again, it's equal under L'Hopital's rule. To the limit as x goes to 0 of, we have to now differentiate this again. So the derivative of secant squared of x, we need to use the chain rule. So that's 2 times secant x times the derivative of secant x. The derivative of secant x is secant x times tangent of x. Divided by the derivative of 3x squared is 6x. Okay, now what's happening? So secant of 0 is 1. So this whole thing goes to 2. And tangent of 0 is 0. So I still have an indeterminate form of type 0 over 0. But one thing I want to do is, if I take the derivative of this numerator as it is, I'm going to have to use probably the chain rule and the product rule. So this part that goes to 2 is kind of irrelevant to this limit. So I'm going to actually separate this out to say this is equal to the limit as x goes to 0 of, and let me pull out the 2 and the 6. So 2 divided by 6 is the same thing as 1/3. So 1/3 secant squared x times the limit as x goes to 0 of tangent of x divided by x. So now this whole piece is just equal to 1/3 because secant squared of 0 is 0. We can do that by direct substitution. This whole piece is indeterminate of type 0 over 0. Again. So we're going to have a 1/3 times, this is going to be by L'Hopital's rule, So we're applying L'Hopital's rule at least 3 times now. The derivative of tangent is, we need the limit as x goes to 0 of, the derivative of tangent is secant squared of x, and the derivative of x is 1. All right, so now we have, see if we can do this by direct substitution. The derivative, secant squared of 0 is 1, so this whole limit is 1. So this is now equal to 1/3. Okay, so now notice that we actually had to apply L'Hopital's rule 3 times in this. And again, at this point, you could have just taken the derivative of this whole piece, but knowing that a part of it was a simple 1/3, we could pull out that piece and treat it separately so that we could just kind of focus on one part of that limit. So again, I want to look at the graph of this. I have pulled in a picture of the graph, and that's the function tangent of x minus x all over x cubed. And at x equals 0, it looks very much like the output gets very close to 1/3.